Hey everybody, Dr. A here, and in this video we're going to be providing some background information on center of gravity, center of mass, and centroid of continuous bodies using the integral formulation. And we're going to be referencing the Hibbeler statics textbook published by Pearson. But before we dive into it, don't forget to hit like and subscribe and be on the lookout for other content like this. All right, let's get started.
In this video, we're going to be discussing the integral formulations for continuous bodies. And we're going to go through center of gravity first, then center of mass, then centroid. Now, as we've mentioned before, there are two types of formulations we can look at when we're performing these mathematical calculations. One of them is for discrete objects or discrete bodies. That would be objects and bodies made up of very simple finite shapes, okay? But in this video, we're going to be talking about the integral formulations, which is really applied to continuous bodies. So that's like a solid object, for example, okay? So let's look at center of gravity first. So the location of the center of gravity of a body is given by the triple coordinates x bar, y bar, and z bar for 3 dimensions, of course. If you have 2 dimensions, it would be x bar and y bar, and then of course 1-dimensional would just be, for example, x bar or just one of the coordinates, okay? So let's go ahead and lay these out. Based on our mathematical formulation and our mathematical framework from the previous video, we're going to have the integral forms as follows. We're going to have x bar equals integral x tilde dw divided by integral dw. And don't worry, I'm going to define these terms in just a second, okay? And then we're going to have, of course, y bar is integral y tilde dw divided by integral dw. And then z bar, similarly, is integral z tilde dw divided by integral of dw. Now, notice this symbol here, x tilde, y tilde, z tilde. What does that mean? That's the first time we're really seeing it here. Well, what these refer to are moment arms associated with our infinitesimal differential weights dw. So from our mathematical framework in the previous video, x tilde is kind of like that x sub I value. It's represented by x sub I, okay? Now, let's make a note of that here so we make sure we understand what we're looking at, okay? We're going to say x tilde, y tilde, and z tilde represent moment arms, okay? Now, in our calculations, when we see an applied problem, we may find that these end up being some kind of function or some kind of distance, okay? So, but for right now, we're just using them as symbols, all right? Now, also mentioned in our previous videos, we can relate center of gravity with unit weight, all right? So here's what I can do. I can say each of these x bar, y bar, and z bar are also can be written as integral of x tilde gamma d volume divided by integral of gamma d volume. And then similarly, I've got integral y tilde gamma d volume divided by integral gamma d volume. And then integral z tilde gamma d volume divided by integral gamma d volume. And then we're going to make a note over here. We're going to say we are relating or relate unit weight, that's gamma, to weight by the following. We say that a differential weight, dw, is equal to unit weight times a differential volume, dv. So where am I getting this from? Am I just making this up? No. This is just the differential version of the equation we saw in the previous video that relates weight and volume by this thing called unit weight, which again, unit weight is kind of like density, except it's weight over volume instead of mass over volume, okay? Now, another thing we want to make sure we understand, we can't just necessarily cancel these unit weights out, because depending on the body itself, you may have different unit weights in different regions of the body. So notice I'm not canceling these gammas out. I'm keeping them inside the integrals for now, okay? So this is center of gravity relations. Now, we can extend this and basically have similar relations for center of mass and then centroid. So I'm going to scroll down, and I already have the center of mass and the centroid formulations already in place, okay? So we're going to scroll down and discuss them. I still suggest strongly that you write these in your notes so you understand them a little bit better. So let's look at center of mass right here, okay? Center of mass formulations, very similar to center of gravity. Notice we have an X bar, a Y bar, and a Z bar. We have X tilde, integral of X tilde dm divided by integral dm. And then similarly, we have something similar, but with Y tilde and Z tilde. We also can relate to density, similarly to how we related to unit weight above. We can relate to density. And how do we do that? We say that a differential mass dm is equal to density times the differential volume dv. And again, all that comes from is saying mass is density times volume, but you're looking at a teeny tiny infinitesimal differential piece of that. All right, so that's the center of mass summary. Maybe pause the video and write all these down in your notes. So next is going to be centroid. Now, before you panic and look at all these, yes, there are 9 different integral equations here, okay? So let's talk about each one. I have organized these into centroid formulations for lines or curves. Lines or curves are in the same category. We could find the centroid of an area, or we could find the centroid of a volume. So this is more, remember, centroid is more dealing with geometric shapes, okay? So let's look at lines first, okay? If you want the centroidal coordinates of a line or curve segment, we have this set of 3 integrals, x bar, y bar, z bar, and we have integral x tilde dl. So for the line or curve centroid calculations, we're looking at a little differential length element along the line that we're interested in, all right? What about for areas? For areas, again, same kind of formulation. We have this x tilde, y tilde, and z tilde. Again, they still represent moment arms, okay? But here we're looking at differential area elements, all right? And then for volumes, same kind of process, except we're looking at differential 3-dimensional, teeny tiny volumetric slices. All right. But if you notice, again, the mathematical framework is the same for all of these. Yes, center of gravity, center of mass, and centroid all represent different physical things, but mathematically they have the same framework. So if you can get comfortable with that, then you should be able to get to the point where it doesn't matter what kind of problem you have, whether it's center of gravity, center of mass, or centroid, the mathematics behind it is the same. It just is physically something different, but you can calculate these things using the same formulations. And again, I just want to make a note, these tilde terms represent like moment arms associated with the differential object that you're looking at for a particular problem, okay? And when we get into some numerical examples, this will make a little more tangible sense. Right now, I know this may seem a little abstract, but again, write this down in your notes, make sure you understand it the best you can, and when we do some examples in the upcoming videos, hopefully a lot of this will be clarified for you.